Yes, Karin, thank you very much for this kind introduction. So, as you know already, my name is Melanie and I'm doing the business development for medical applications here at Axetris. We have already a few customers using our LGD Compact for breast gas analysis, and today I want to show you the idea behind this application. Let's start firstly with the situation in diagnostics today. So normally you just go to the doctor when you are feeling bad or uncomfortable. And at the doctor's office, they have to do then several types of diagnostics to find out where it comes from. And some of these methods will take a while till you get the result. And during this time, you may get nervous about the results. In a worst case, then, you may get a bad result where you have to go through several treatments to get healthy again. But in general, you can say if you have already symptoms, the disease is often progressed. And this also often reduces the chances of recovery at the same time. And as a last result, treatments also become more expensive and more complex. But let's also take a look at the diagnostic methods commonly used today. Many methods are often painful for the patient, and for some people this can start just with a simple blood sample. Other methods, such as diagnostic imaging, sometimes require very expensive equipment and are therefore very costly. In addition, some methods require more time and effort for further processing and evaluation, and they are therefore time and also personnel intensive. This is often the disadvantage that we as patients have to face when we are not well and the diagnostics turns out to be difficult. To understand now how breath analysis might help here, we need to understand a few simple medical basics. So basically, every disease somehow interferes with our metabolism. But we can also influence this metabolism through our diet or lifestyle, for example. This then results in a change in our metabolic products. It can be more or less or even completely new ones. This always depends on the process behind. And since every organ in our body is connected to the bloodstream, these metabolites are therefore also released into the blood. And this is why, for example, inflammations can be detected in the blood. And for sure, the same applies to other diseases like cancers, which are detected by tumor markers. And through our bloodstream, this blood from the body first passes through the heart and then continues to the lungs. And in the lungs, the blood then passes the so-called alveoli, which are the smallest air sacs in the lungs. And this is also where the gas exchange takes place. Gas exchange here means, so to speak, the old air from the body goes out and the fresh air goes in. Fresh air is clearly oxygen, which goes from the lungs into the blood. And the old air from the body can contain many things, depending on the metabolic products. CO2, for example, is a waste product of the body that is always removed. But also many other gases occur, methane and ammonia, for example. Most gases in the breath are summarized under the term VOC. And this means volatile organic compounds and refers to their organic origin. Sure, that was all very theoretical, but let's take a look now at an example that many people may know from their circle of friends or family. And this is about the intolerance of lactose. Let's first see how the process works in people without lactose intolerance. Here the body has the enzyme lactase, which allows it to split lactose into two simple sugars. And these sugars can be then digested further in the intestine. But how does this work for people with lactose intolerance? These people do not have this enzyme lactase. In order to process the lactose as a complex sugar, the intestine functions like a fermenter. That means sugar is therefore fermented, splitted into its components. And in addition to fatty acids, also gases are produced. In this process step, these are only hydrogen and CO2. but there are also people with bacteria in their intestines that process this hydrogen further into methane. And to avoid false negative results in diagnostic, methane must be also measured. And this is, for example, an application that our customers solve already with the LGD Compact. But to be honest, do we know many other examples from medical practice where we can recognize diseases with our breath? Certainly, there is capnography, for example, where the CO2 in the breath is monitored. But this is not necessarily used for diseases. If you move in the scientific circles, breath analysis is a very important topic, but this method is still in its infancy. Nevertheless, this method is very promising, and the number of diseases that could be detected is huge. Here are just a few examples of what science is working on. For lung cancer diagnostics, for epilepsy, for Alzheimer's disease, for sleep apnea, for renal failure, and nevertheless, we have 2021, and I think everybody knows already about that, also for COVID-19. You see, there are many, many possibilities. But let's not just talk about science. Let's take a look at real figures. Here you can see the statistics of the causes of death worldwide in 2016. But not only diseases play a role here, but also, for example, traffic accidents or natural disasters. Let's focus for the moment on the diseases. Here, marked in red, you can see the diseases that can be diagnosed with the help of breath gas analysis, according to the current state of science. And this is very early in contrast to other methods. If we just look at the example of cancer, this disease causes about 1 in 6 deaths worldwide. And especially with cancer, early detection plays a very big role. According to medical experts, about 30% of all deaths could be prevented if cancer were detected in time. And when we have a look now on the market, you can see that many applications have already found their way into the real medicine. As you can see here on this world map, there are already many companies that deal with breath gas analysis. And some of them are already using the LGD Compact very successfully in their application. But now the question arises whether the LGD Compact is the best solution for every application in breath gas analysis. And there is a very clear answer to it. Of course not. So, at the moment, most of the breath analysis still takes place in research. And here it is important to record the entire footprint of the breath. The goal of research is to specify individual biomarkers for diseases. And for that, you need an overview of all components in the breath. Hardly any other technique is better suited than mass spectrometry for this. And we can never replace this with TDLS technology. On the other hand, there are the devices for home care and the so-called wearables. Here the sensor technology must be very, very small and, above all, also very low priced, since these devices are designed for the consumer market. And for this, TDLS technology is of course much too expensive, since we even use lasers. But right here in between, there is a market that is very well suited for the TDLS technique and the LGD Compact. These are small devices for diagnostics in medical practices or hospitals, for example. Here we are talking about the detection of individual diseases. So we are talking about these specific biomarkers. And these can be often detected very well with the TDLS technology. And in addition, the price for the LGD Compact often corresponds exactly to what the sensor technology in such devices is usually allowed to cost. But why does the LGD Compact or the TDLS technology in general work so well for this? As I mentioned earlier, our breath consists of countless substances. So to make it even more complicated, these substances often vary from person to person. Here you can see a list of the VOCs most commonly found in breath. And this is only a very small part of what can be contained. So you see, the gas matrix in breath gas analysis can become complex in any way. And this complex gas matrix can be the part where TDLS brings an advantage. In the left diagram, you can see how such a gas matrix could look like in the infrared spectrum. These absorption bands of the gases are partly very close to each other or even overlap, and this can lead to cross interference. In the right diagram, you can see an enlarged section of the absorption band of gas 3, the blue one, which is supposed to be now our target gas. The red peak is our laser with a fixed wavelength. So we can easily tune these laser wavelengths by changing temperature and use it to scan over the gas peak we want to measure. And with this narrow laser beam, we can scan specifically over individual gas peaks and avoiding therefore cross interference with other gases. And in addition, if there's a second gas in this range that we want to measure, we can also extend the tuning range of the laser a bit. And this makes it possible sometimes to measure also 2 or in some cases also 3 gases simultaneously. CO2 is a very good example for this, as CO2 and CH4 overlap in the spectrum. Depending on how deeply we exhale, the CO2 content also changes, and therefore CO2 is often used as a correction factor in breath gas analysis. I have here on the left side a measurement from an LGD calibrated only for CH4, but not for CO2. And in this diagram, you can see the measured CH4 when we add only CO2 and nitrogen to the gas cell. With increasing CO2 level, the CH4 concentration increases slightly. So we have an influence from the CO2 peak in the spectrum on CH4. Let us now take the LGD calibrated to CH4 and CO2. That means we have 2 target gases. Here the CH4 remains stable, no matter how much CO2 is applied. Another good example of cross-interference is carbon monoxide. Carbon monoxide is often present in the breath of smokers. This gas is outside the spectrum of CH4. Therefore, it does not interfere in TDLS in the measurement. We can see this well in the diagram. The TDLS curve is the red one. Here you can see a CH4 measurement which was made before smoking. These are the left 2 measurements, and after smoking. These are the right 2 measurements. And the CH4 is not influenced by CO and remains stable with the TDLS technique. Another optical spectroscopy method is NDIR. This is a blue curve. And here a broadband source and a filter is used instead of a laser. However, this filter cannot limit the measuring range so precisely like we can do for TDLS. And therefore, there is an often interference from other gases that are close to the target gas. And this can be seen very well in the measurement after smoking, where the CH4 content rises. And with that, I would like to end my presentation as I began it. Only this time with a scenario of how we could improve our lives a bit with gas measurement technology. So imagine, once a month you think about your regular checkup. But you don't have to go for the doctor just for that. Maybe a pharmacy or a health center would be enough. You would have many options. And there is a device in which you only have to blow in briefly. This data is then forwarded directly to your doctor, and will be evaluated automatically. And this happens month after month after month. And at some point, the computer registers a change in your breath sample. Your doctor would then contact you by himself. And all this very long before you notice anything of the disease yourself, long before you have symptoms. The chances of recovery are often much better at this stage. You see, gas measurement technology can be very helpful to us in many aspects of life. And with that, I will end my presentation, and I'm looking very forward to an interesting discussion with you. Thank you very much.